All right. So this is class number 4. And remember that at any point during the semester, if you want to know where we're at or where it fits in the context, here I'm holding up our course schedule. I've printed that out and it's posted on Blackboard, and I have a paper copy of it that I keep here in my office just so that I personally can refer to what the topics are and when assignments are due. So I really think this is a useful thing maybe to put as the very first page in that 3-ring binder that I've suggested you prepare. I think probably this is more important than the syllabus itself in terms of how often you're going to refer back to it during the semester. I hope you've already got the textbook, and if you've printed the notes and in-class exercise, which I encourage, please include those in your 3-ring binder. All right, so homework 0 is finished. I was taking calls hot and heavy on Friday. I hope that I called everyone back that I had to temporarily put on hold, because at one point I actually had 3 students calling me simultaneously, and I was trying to write down as quick as I could. But if you didn't have a chance to talk to me, just to make sure that you understand how to place a Teams call, feel free and do that today or whenever, just so that we can make sure that you've got it figured out, and so that when you need help on questions from homework 1, for example, you'll know how to do that. Speaking of homework 1, that's due on Wednesday, and it's due before class. And so your submission deadline is 11 a.m. on Wednesday for homework number 1. And I've already got a few good questions, so I can tell that some of you are early birds and you're working ahead. We're going to cover a few additional supporting topics today that will make homework 1 even a little bit easier to complete. I hope that the in-class exercises until now have supported you as you've done homework 1, but we'll look at some new stuff. Now, as a reminder, you need to submit that as a single PDF file. It shouldn't be a JPEG image. It shouldn't be 5 different PDF files because you had 5 different pages. It needs to be one single continuous PDF file. And if you're using the Cam Scanner app, it makes it really simple to do that. So submit that black and white PDF file to MU Online before 11 on Wednesday. So before we start talking about economic equivalence, are there any questions related to the announcements? Feel free to interject with your microphone, or if you're real shy, you can type your question, but I think it's just maybe more immediate and less awkward if you don't mind speaking your questions rather than typing them into the chat. I sometimes miss those. All right, so what I mean by economic equivalence is this is how we deal with the time value of money. Now that phrase, the time value of money, you should be able to, by now, write like a paragraph on what that is, the time value of money. And I've addressed it already a couple of times in our lectures, but in case it's not coming to mind immediately, what that means is the fact that prices are always going up over time means that money in the future is less valuable than money now. And so if you're going to be getting income in the future and you're spending money now in order to make that income possible, let's say you're investing in new equipment for your company, the question is, how much can you afford to spend on that new equipment now if you're going to have a certain amount of revenue in the future? And so the time value of money is just this continuous erosion of purchasing power of an individual dollar that comes from inflation. And so economic equivalence is trying to figure out some amount in the future, how much is that worth now? All right, so let's go over a couple of important terms here. When we say present worth, that means the value of the money now in the present at time 0. We looked at some cash flow diagrams in the lecture on Friday, and time 0 means the present. And so sometimes the present worth is also referred to as the present value or net present value, discounted cash flow. This word discount, you maybe have seen the word discount referred to in a retail sense. Like if you go to Marshall's, you can buy clothes at a discount compared to what they originally cost at a department store. Here we mean discount something more specific. We mean just that as money in the future, a certain amount of money in the future, let's say if I promise to pay you $100 in 5 years, how much is that worth today? It's not worth the same amount because $100 in the future isn't going to be able to buy as much as $100 now. And so if you're moving that $100 5 years from now into an equivalent present value, then you'd have to discount that. So discount implies it's going to be worth less as you move it backwards in time from the future to the present. Future worth is that single amount that I've just, in the example where I was saying you'd get $100 5 years in the future. If it is an amount in the future, we call that either a future worth or a future value. And both present worth and future worth, when we draw a cash flow diagram, that's going to be a single arrow. So those are individual amounts. Those aren't recurring amounts. Because those recurring amounts, where it's a series of arrows that all have the same height, those are annual worths. And so it's consecutive, meaning that it's year after year without any interruptions. So that's consecutive. Equal, meaning that each of those arrows in the cash flow diagram, which represents amounts, they have to be the same height, meaning it's the same amount. And then end of period amounts. So the end of period assumption is just that during a month or a year, all of your revenues and all of your expenditures are kind of aggregated together and represented by an end of period equivalent of those payments and revenues during the period. And so we take them all to a single end of period time. So an annual worth is also sometimes called a uniform series or a uniform annual series. And it just, the components of that is it's consecutive, equal, end of period amounts. Economic equivalence is combining the idea of an interest rate and the time value of money to find out how different amounts of money at different points in time are economically equivalent. So, for example, 100 does not equal 90. We know that 90 and 100 are two different numbers. But what if the 90 is now and 100 is in the future? Well, because of the passage of time and the effect of the interest rate, 90 now might be the same as 100 in the future if the 90 is earning interest in the intervening period. So that's economic equivalence, is two different amounts spaced out through time. So in order to determine the economic equivalence, we would use a certain interest rate and a certain amount of time to relate amounts of money. So you can think of it as that there are four key variables when determining economic equivalence. There's the interest rate, number one. There's the amount of time, number two. There's the amount at the present, number three. And the amount in the future, number four. Now we can also do economic equivalence with annual series, but just for simplicity, we'll begin by doing these economic equivalences between present and future. And in fact, we've already done many of them. You are already determining economic equivalence without really having that term defined for you yet. The symbology that we apply to economic equivalence is up on the screen there. And you've seen these labels before. T, time, N, number of periods. Here's all these variables we've used before. Now, interest rate, we have to be a little bit careful with, because often interest is quoted on an annual basis, but that's not the only way to quote interest. Interest can be quoted on a monthly basis or on a quarterly basis. And so strictly speaking, I is defined as the interest rate per period. And a period may be a year, but it's not always a year. And so like one of the curveballs I'll throw at you occasionally this semester is I'll tell you the interest rate on an annual basis, but then in the problem statement somewhere else, it'll make it clear that interest is being compounded differently than annual. And so you'll have to divide the interest rate per year by the number of periods per year. So we'll get to a few of those, but I just want to make it clear to you that you need to double check how often is the interest compounding. Is it annually or is it a different time period than that? All right, so economic equivalence visualized. Here's a cash flow diagram. We can see that with the arrow going down, that means from the perspective, whoever's perspective this is. If this is our perspective, that means that we have to pay 100 now at time 0. And it looks like our applicable rate of return for this cash flow diagram is 10% per year. And so the question is, if you're going to pay 100 now and you have a 10% interest rate, then what's the economic equivalence in the end of that intervening time period? So at year 1, then it should be 110. So these two are equivalent, meaning that if you have an outflow now of $100, then you should receive an inflow of $110 a year in the future. So it's economically equivalent if 100 equals 110. Normally that wouldn't be true. 100 equals 100. But 100 equals 110 if that 110 is in the future and an interest rate has been applied. So if you remember, I used that term earlier in the lecture, discount. If you take the future amount of 110 and you discount it by 10%, then 110 discounted by 10% 1 year would make it $100. So that's the other way of looking at it. Sometimes we think about compounding is when the number gets bigger in the future. And so 100 compounded 1 year to the future is 110. 110 discounted 1 year into the past, meaning we're going left or backwards through time. If you discount 110, then it becomes worth 100 after 1 year. So now we've used that compounding and discounting those verbs to give you a sense of whether we're talking backwards through time or forwards in time. So in words, what this cash flow diagram is illustrating is that $100 now is economically equivalent to 110 1 year from now if $100 invested at a rate of 10% per year. So those two are economically equivalent. Now, one other point that I'll make is that we're not saying that a withdrawal and a deposit are the same thing. And so it's economically equivalent because the magnitude of those two lines are the same over time. You know, if you discount 110 to time 0, then it becomes an arrow upward with a length of 100. But we're just, in this illustration, talking about the equivalence of the magnitude. And so deposits and withdrawals aren't the same thing, obviously. Getting money isn't the same thing as having to pay it. All right. So you can receive 100 in 1 year or a certain amount today. For 10%, how much is the amount you should receive today? Okay, so this is, we're discounting $100 from the future to the present, and the interest rate is 10%. Here is the formula for that. This is a formula you've seen before that relates future amounts and present amounts. And so this 100 is F. So F equals 100. P is unknown. And I, we have to express as a decimal. And so here in this formula, you couldn't say that I is 10. You wouldn't write 10 in for I, but I would rather be 0.10. All right, so if you rearrange that equation to solve for the unknown is the present amount. So future divided by 1 plus I to the n power. And so the present value of $100 is $90.91. So it may be tempting to say, well, the present value is just $90, you know, because you think it's a 10% reduction, but that's not exactly it. You have to solve for this, and so you'd need to have $90.91 in the bank in order for it to compound into becoming $100 in the future. Because if times 0, if it was only 90, then what's 10% interest of 90? It would be $9 additional. And so if you had only deposited 90 at time 0, then it would become 99. And we want to know how much do you have to have at time 0 for it to become 100 after a year. And so you have to have $90.91 for it to turn into 100 from 10% interest being added. Okay, here's a couple of cash flow diagrams, and we're going to develop a really compact language for describing the types of problems we need to solve. And so what's illustrated in this first cash flow diagram is we want to find a future amount. And remember, the clues that I've said for how we kind of summarize these cash flow diagrams is it has the dashed line. So the dashed line, and then the question marks also emphasize that this is an unknown. So we want to find the future amount, and we're given a certain amount in the present. So the way that we summarize this is we say it's find f given p, or f divided by p. And the reason why we say f divided by p, why we follow this convention, is that there are a series of formulas that will allow us to solve for the unknown. And so it's advantageous if we have the unknown in the numerator of the ratio. F divided by P, that's going to be a ratio. It's the ratio of the unknown future amount to the known present amount. So to solve for F, we'll move the present value over to the right-hand side of the equation that I'm going to show you in a moment. But for now, the important point on this slide is just if you have a cash flow diagram where there's an unknown, the way you should think of that is that you're trying to find F given P. And so this, how would you describe this problem? It's different from the first. Find something given something. Okay, so in this one, we're find P given F. And so that's going to be a P/F problem. So you always have the unknown in the numerator of the ratio. You're going to have the ratio of the unknown to the known. Okay, so now this is an annual series and a present value. And so in this case, it's find A given P, because A is the unknown, P is the given, so that it's A/P. A divided by P is the ratio that we'd want for this. Okay, and finally, how would you phrase this or summarize what you're seeing in the cash flow diagram? We'd summarize it as find P given A. Good, Jonathan. Find P given A. All right. Now, no interest rates were specified in each of these illustrations. It's just we're trying to identify what's the problem type. And to give you a clue of where this is headed, you may have noticed that your textbook, in the back of the book, in the appendix, has page after page of table. Let me see if I can grab the textbook off my shelf, and I'll show you what I mean. All right. So here's the textbook, and in the back of the book is page after page of table. And so there's a 3% table, a 4% table, 5, 6. So each page is a different interest rate, and then these different columns are P/F, F slash P, A slash F, F slash A, and then each row represents a number of periods. And so this appendix, the series of page after page of table, is very useful in problem solving. So if you know, if you know the ratio of P slash F, then you can go to your book, find a decimal, and then very quickly calculate the unknown. So that's kind of why we bother to set this up as a ratio. You may be wondering why the emphasis on reducing a problem type to just this kind of a ratio notation. It's because then we can go to the textbook and find really useful like kind of the solved ratio and find the unknown quickly. All right. So with this, what we're going to do is look at the in-class exercise for today. And I hope that you've printed that. Just to reiterate, if you're wondering where these are, it's available in Blackboard. Let me even take a moment to show you that. I'll bring it on the screen here real quick. All right, so I think there may be one or two students who've just joined the course maybe in the middle of last week, and so the in-class exercises are here, and then if you click on all ICE papers for fall 2020, then it'll bring up. And so today we're going through in-class exercise number 4, economic equivalence and cash flows. All right, so the approach we follow for these is I pause from talking for a moment. We'll take the first 2 together today. And what I suggest you do is, if you like, you can type what you think is the answer down there in the chat box as you try solving it. And I'll give out smileys or stars or hamburgers, or who cares about that. But anyways, I'm going to pause for a moment and give you a chance to digest these problems. We'll talk through them together, and I'll bring the solution up on screen in a couple of minutes. Your calculator, it's easier just to wait until the solution comes on the screen and to write it down. And you may think it's going to, in the end, be the same either way, but it is better if you try solving them yourself. And Casey's got it right. So good job there, Casey. All right, let me bring up the solution on the screen. Okay, the first one, we are looking at the, yeah, good. Because that's all I can give you, Casey. I can't give you a real hamburger at this point, but I can give you a sticker hamburger. I need to diversify if I'm going to be doing that. Okay, so the owner of the construction company is going to buy a new cement mixing plant. Cost $550,000. So that will be done at time 0. So how do we know to put that at time 0 rather than some other time? Because this owner is just thinking about it today. She's not necessarily actually buying it today. Well, by definition, when the first thing that happens is an expenditure, that's when we begin the passage of time. So the revenue of $85,000 a year, what we're saying is that each of the years after the purchase of the machinery is going to have $85,000 worth of revenue. So the outlay or the outflow of cash, a P, has the labels. Remember that in order to be strictly correct, we need to have the labels included on these cash flow diagrams. So the present value is $550,000 in outflow. And so in the future, there will be an annual series. Now, it says that for each of 6 years, it's $85,000, and then in the 6th year, it's $50,000. So what some of you may have done was combined this last year, and that's fine. You can do that. So there's 2 different ways to summarize this. We could say it's an annual series with 6 years of A, and A is $85,000. Or you could say it's a 5-year annual series at 85,000, and then a single future value of 135,000. So either one of those is correct. I typically will leave the annual series uncombined, and I'll just have that single future value kind of out by itself. And so you can see that this arrow is on top of the other one, just to illustrate that those are two different things. There's the revenue you got from operations, and then there was the scrap value for selling this construction, the cement mixing plant. So that's why I don't combine them, is, what if we get an updated value for the scrap in year 6? Then it would be easier just to change the one component than the entire combined amount. But it's the same. Any questions about this first cash flow diagram? All right, so question 2, you want to receive 95,000. That means the arrow should be up 1 year in the future. And it doesn't say 1 year, it says next year. So that means 1 year from now. If you want to receive 95,000 from an investment that offers 9% annual interest, draw the cash flow diagram that illustrates this situation. And how much should you deposit today? So the unknown is the present. So we have a dashed line on that arrow, P equals question mark. You can see somewhere I've put I equals 9%. It could be below the line. It could be this side of the line. Just somewhere we need to, if the interest rate is defined in the problem statement, we need to include it on the sketch. And so if you apply that formula, then you'll get the interest is, the present value you need to deposit is 87,155.96. And again, we need to calculate the answer to the nearest penny. On a problem like this, where you're using the equation, you can be precise to a penny. When we start to use these textbook tables that I was mentioning earlier, we'll do all of our calculations to the nearest penny, but then sometimes we may need to round off, because in these factors, some of them only have 4 significant figures. And so then, if we were having to round off on this problem to 4 significant figures, then that would be 1, 2, 3, 4. So we'd have to round this to 87,160 if we had used the factor method. But in this case, since we're using the equation method, we can be accurate to the nearest penny. All right, the next question. Now this is a little bit of a head scratcher. This is kind of just, basic problem solving. I'm not going to tell you how to solve this one, because there's a couple of different ways to prove which way is better. Now here's the background. Fuel prices are low right now. Gas prices went up a little bit over the last few weeks. I filled up for $1.79, I think, 2 or 3 weeks ago, and now it's up to like $2.29 at the place that I drove past this morning. So it's a little bit higher, but I mean, it's not bad at all historically. I remember driving cross country back in 2008 in a gas hog when the average fuel price was like $4 a gallon. So we are sitting pretty right now. So sometimes when gas prices are especially low, I wish that there was an easy way to store fuel. Back when the pandemic first hit, I saw a couple of days the gas was $1.50 around here. And up by where my parents live, there were a few stations up there that was selling fuel for 89 cents. So it's ridiculously cheap. It's not convenient to store fuel at your house, but there are commercial places where you can store fuel. And so in this kind of hypothetical, we're saying that the price of fuel is $2.20 per liter for aviation fuel. In 3 years, we expect that the cost is going to be higher. We expect it's going to be $2.65 per liter. Now, in 3 years, we know that we need to have 100,000 liters of fuel available. So either you can buy the fuel now at this low price and then store it, or you can invest the money you would have spent on fuel and then use that money in the future that presumably is also going to include interest. You're going to save money and then earn interest, and you'll have this big pot of money in the future. You'll buy that at the higher price. because in the future gas is going to be more expensive. So which is better? Is it better to buy the fuel now and store it? Or is it better to save the money and buy the gas at the higher prices? All right, so I'm going to pause for a moment, and you find a way to prove which is better. Without describing exactly how to solve this, I think, if you're sometimes not sure how to proceed to solve it, like if you don't have a clear path to the solution, just start calculating things. It's better to calculate something, and it'll maybe trigger an idea. So for example, you know how much gas you need, you know the prices now and in the future, so you can find out how much do you need to spend now. You also can find out at the future cost, how much are you going to have to spend then. So that's one thing you can calculate, and maybe it'll be useful. Probably it'll be useful. Another thing you can calculate is, let's see, Casey. All right, Casey's going through the proof here. The only expenditure you'd spend is the fuel cost, whereas if B, you treat it as an investment. Okay, so it's kind of like you'll have money left over. If you invest the money, buy your fuel, then you're going to have extra cash left over. And Casey mentions the 53,000. Yep, that's the remaining amount that you'll have if you invest the money and then you buy the fuel with it after 3 years. So let me bring my solution up on the screen. We've seen the number already. Oops, wrong one. Okay, there we go. All right. So if you buy it now, how much is it going to cost to buy the fuel? All right, so you're spending $2.20 per liter, and then you also have the storage fee. So to buy the gas now and have it in that, it's probably a big storage tank somewhere. In order to have that fuel in the future, it's going to cost you $259,999.99. All right. Or part B says invest the same amount of money into a savings account. So what that means is the amount that you would have spent to buy and store the fuel, put this in a savings account that makes 7% per year. So how many dollars do you have after 3 years? And remember, this formula allows us to account for compounding. So N of 3 means that every year the amount is going to grow by 7%. And so then the next year after that, it's 7% of the previous year's total, including the principal amount that was at the start, but then all of the compounding. And I've done this thing here where I include the intermediate steps rather than just putting it in my calculator and hoping I didn't make like a finger slip or a mistake. I think it's a really good habit to write the intermediate steps. And so what this illustrates is that the factor 1.225043, that is how much it's growing over the compounded period. So if I invest the $259,000, I'm going to have $318,000, and so I'm going to have money left over. After I buy 100,000 liters of fuel at the higher rate, the cost of that fuel is only $265,000. So rather than buy the fuel and store it, it's better to just invest that same amount of money. Another way to look at this, John mentioned, is that if you have this $318,000, think about how much fuel you could buy. You could buy more than 100,000 liters of fuel. You'd be able to buy 122,000 liters of fuel. So that's the other way of kind of proving that it's better to invest, is that your purchasing power is going to be greater. After 3 years, that amount that now you can only buy 100,000 liters of fuel, if you invest it, your purchasing power is going to be greater because you'll be able to buy 122,000 liters of fuel. Or just buy the amount of fuel you need and have leftover money for other things. So the answer is it's better to invest and then buy at the higher price. Now why? It's because the cost of fuel is going up less than 7% per year. If we were going to find the annual rate that the fuel cost is going up, that annual inflation rate of the fuel cost is lower than the savings account is paying. And so it's better to let the savings account do the heavy lifting. The money will grow faster than your expenses, then let it. All right, any questions on this before we move on to the fourth question? Any questions at all? All right. Here's our fourth question. All right. How much should you pay in year 4 if you receive 4 equal payments of 12,500 AED? And you've seen that before when we did the one of the earlier in-class exercises. That's the United Arab Emirate dirham. So 12,500 dirhams. How much should you receive in year 4? So here in the cash flow diagram, you can see that arrow down. I guess it would have been better if I made that a dashed line because it's an unknown amount we're trying to solve for. So you pay out 12,500, including in the 4th year. That's kind of weird that you would pay 12,500 and right at the exact same moment you're going to withdraw the equivalent balance. But the reason why I've asked the question this way is because this is how a find F given A type annual series is expressed. There's a standard convention for how we summarize finding an equivalent future value for an annual series. And the standard convention is that the annual series includes the year that the future value is paying out. So here, what I would like you to do is calculate how much should you pay? What is the future equivalent there? And the way I'd like you to solve this at first is just with the formula. Hold on 1 second here. Oh, I gotta hide that. I don't want you to see the answer yet. All right, so the first part is compounding it into the future. And so this 12,500 in year 1. So this amount here, how many years does it need to go to contribute to year 4? So it's moving from 1 to 2, so that's a single year. From 2 to 3, that's 2. And from 3 to 4, that's 3. So compound 12,500 at 5% 3 years into the future. So remember our formula, F equals P times 1 plus I to the n power. Let me bring that back up on screen because I think we've seen it today. Here it is. F equals P times 1 plus I to the n power. So here on this in-class exercise, what we're saying is let's treat this year individually. From this year, let's move them each to the future. And then the 12,500 that's already in year 4, that doesn't need to be compounded at all. But for the rest of them, calculate their individual contributions to how much is going to have to be repaid in year 4. So it's going to be 1 plus I to the 3 power, 1 plus I to the 2 power, 1 plus I to the 1 power, and then 1 plus I to the 0 power, which just means it's the amount itself. All right, so let me pause for a moment, give you a chance to try and calculate how much each of those individual amounts compounded to the future are, and then sum them together to find out what is F. All right, since we're running low on time, let me bring the solution up and show you how this all fits together. I know a lot of you are already getting it, but probably some people are still a little bit puzzled about this. Okay, so I've labeled each one of these arrows with a letter. So there's A, B, C, and D. And so the future value of A is we're taking 12,500 and compounding it 3 years into the future at 5% per year. So its future equivalent for just that single arrow is 14,470. And we do a similar thing with the arrow B, except for that now it's only fewer years because it's not as far away to year 4. So it's being compounded 2 years. Arrow C is being compounded 1 year. So then you add them all together, arrow A, B, C, and then D, and the cumulative amount is 53,876 and 56 cents. So that's one way, is to treat them all individually, like we're doing a bunch of find F given P. But this is an annual series. We don't have to do it individually. So the other approach to solve this, as it says in the handout there, try using this. Now, I've never showed you this formula before, but what it is it's F/A, so that's the ratio, is equal to 1 plus I to the n power minus 1 in the numerator divided by I. So let me show you how that works. The F/A part of it is just saying A is 12,500. F is unknown. The interest rate, 0.05, n equals 4. So we define the variables, and then the formula is, it's the ratio. On the left side is F divided by A. So that means if A is given, we just move A from the left side to the right side of the equation. So now it's in the numerator of the right side, and multiply it by this whole factor. So you can see the substitutions that I've made. Here's the equal annual series, which is consecutive amounts. And then in the end, we get the same value as we did when we treated it individually. And so, it's much simpler. If you have an annual series, just go ahead and treat it like an F/A. All right. It's 11:50. We're out of time. I've got to give you time so you can walk to your next class, wherever that might be. If you have questions, remember, reach out during my office hours. I'll be glad to hear from you. We will continue on Wednesday, but just to look one last time at these announcements, between now and Wednesday, you need to finish the homework assignment. It's due before class on Wednesday. All right? So if you have questions, get in touch. I hope you have a great day. Bye.